In this video, we are going to look at integration by completing the square. So let's look at the first problem that we are having today. So problem number 1, having integral of square root 3 minus 2p minus p square dp. So here we have to realize that our operational variable is p and we are used to having x, so just consider that p as x, so everything still works the same. So the best way, if you want to apply completing the square, it's better to rearrange what is inside the bracket there. So we will just extract it and work with it aside. So we will have negative p square minus 2p plus 3. So before we complete the square, we can factor out negative. Then we will have plus p square plus 2p minus 3. Then we still have the negative outside the bracket. Then we can complete the square now. Remembering that when we complete the square, we first add the coefficient of the middle term divided by 2 and then squared. Then we still have 3. Then we have to subtract the coefficient of the middle term divided by 2 square. Then now we go and simplify. We'll have 2p, then plus 2 divided by 2 is 1. 1 square is still 1. Then we still have negative 3. So this also will give us 1. Then from here, it's better to consider this part separately, then rewrite it in a squared form. So if I do that, I will have p plus 1 squared, all squared. Expanding this bracket will take us back there. Then we will have on the other side, negative 3 minus 1 is negative 4. So that's it. We have successfully completed the square. Now what we need to do is to go and put it back inside our integral. Then we must not forget that negative also. So we have p plus 1 squared minus 4 dp. Then from here, we can go and look at the corresponding formula that will help us to integrate this. But before we can do that, it is better to actually distribute that negative inside the bracket. And if we do that, we will have plus 4, then minus p plus 1 all squared dp. Then also I can rewrite that one for the last time in another form, which will be the integral of square root of 2 to the power 2, which still gives 4. It's just rearranging it in another way. Then from here, we have dp. Now what we need to do is to go and look at the formula that can help us to integrate this, because of course the formula is there that corresponds to this integral. And this is the formula: integral of f prime x square root a square f of x square dx. So now we consider, in the place of x, we consider that p actually represent x in this case. So this is equal to a half f of x square root f of x all squared. It starts with a squared, not f of x here. It's a squared. It's a bit long. F of x square plus a half a squared arc sine f of x over a plus c. So that is the formula that corresponds to that, and we can prove that by saying that if we say that our f of x is actually now p plus 1, then f prime x, it's actually, when we differentiate p, actually we can just say it's supposed to be actually f prime p, but let's just let's not try to change variables. So when we differentiate p, we will get 1 if we're actually differentiating with respect to p. Then a, it's actually 2. So what we need to do is to go and substitute back into the formula. Then we are going to have, we write our integral dp, then this will be equal to, we check on the formula there, we are having a half f of x, we say that it's p plus 1, then square root our a square, it's actually 4, so we don't really need to write it in a square form, we can just say it's 4, then minus our f of x is actually p plus 1 square, then plus a half, then a square, it's actually 4 because it's 2 to the power 2, then arc sine, then p plus 1 over a, it's 2, then plus c. And this can be simplified, but it's good enough right now. Simplifying is not going to be a problem. We can just rewrite it in a nice format. Now we can have p plus 1 over 2, then square root of 4 minus p plus 1 all squared. This side will 4 divided by 2, it's actually 2, then arc sine p plus 1 over 2 plus c. So that's it. We have successfully integrated by completing the square. Then we can look at another problem where we can apply completing the square. So this will be problem number 2. So integral of 3 dx x squared plus 2x plus 10. So this one is a definite integrals because it has limits of integrations. So we need to integrate and substitute the higher limit or the upper limit, which is 2, and the lower limit, which is 1. So if we complete the square like we did in the previous example, let's take this one and complete the square separately. So we'll have x squared plus 2x plus 10. Then we'll have x squared plus 2x. Then we take the coefficient of the middle term, which is 2, divided by 2, then square it, plus 10. Then we subtract it this side. Then simplifying here, we have 2x, 2 divided by 2 squared, it's still 1, then plus 10. This side will have minus 1. And these ones here, we can consider separately. Even this side, we consider separately. And then what do? We can rewrite this in a square form. Then it's going to be x plus 1 squared. Then 10 minus 1, it's actually 9. Then from here, we take back our integral as it is. Then we'll have 3 dx over. Now we write the completion of the square form, which is that. And we can factor out 3 here so that it's written like this. Then we will only have dx there. Then x plus 1 all square. This one, 9, can be written also in a square form to be 3 to the power 2. So we can see that this we can go and try and read in our formula sheet. And the formula that we can use, it's actually integral of f prime x over f of x square plus a square dx is equal to 1 over a arctan f of x over a plus c. So in this case, we can see that f of x is actually x plus 1. Then a, or let me start by differentiating f of x. F of x prime, it's 1. Then a, it's actually going to be 3. So what we need to do is to just go and substitute everything here. Then we can see that here we have 3, 2, 1 dx, x plus 1 square plus 3 square. So it's going to be 1 over a is 3. Then arctan f of x, it's actually x plus 1. Then over a is 3. Then we close that there. Then because we are actually working with definite integrals, there's no need to write plus c. Then we can actually put 2 and 1 there. Now what we need to do is to go and substitute and ensure that our calculator is in radian mode. And then here we must not forget this 3. So this 3, it's still there. So it means that it is actually going to divide here. So this term 3 and 3 is gone. So we are only going to be left with only arctan, because we had a 3. So it's going to affect there. Then we will substitute firstly we substitute 2 into x. 2 plus 1, it's 3. So this side will have 3 over 3. It's actually 1. Then minus arctan. Now we substitute. In the place of x, we substitute 1. This side will have 2 over 3. Then we evaluate. Then we get 0.197. And the calculator should be in radian mode, unless if it was given as 2 degree or 1 degree, it can be in a degree mode. But in this case, you have to put the calculator in radian mode. So let's go and look at another integral. So today we want to do a couple of integrals. So this is going to be number 3 now. Integral of dx over 1 minus 4x minus 4x squared. And we are still completing the square. So we want to complete this square until we know how to perfectly use it in different cases that can be given in different questions. So in this case, we can see that 4x squared is on the third term. So we can rearrange it like we did on the first problem. So we will have negative 4x squared minus 4x plus 1. Then in this case, instead of factoring out negative, we can factor out negative 4. Then we will have x squared. Then here we will have plus x. And then here we will have negative 1 over 4. So now we have factored out negative 4. We still keep our negative 4. Then we have x squared plus x. The coefficient of the middle term this time around, it's 1. So plus 1 divided by 2 square minus 1 over 4. Then we can subtract what we added there to balance the equation. So it's better to use square brackets because we have normal brackets inside there. Then we have negative 4 x squared plus x. This works out to 1 over 4, then minus 1 over 4. Now we need to work out this here. Then what does it give us? So we can do it on the side. It's more like we have negative 1 over 4 minus 1 over 4. It's actually going to be negative 2 over 4, which is going to be negative 1 over 2. So it works out to negative 1 over 2. But you can do it with a calculator. I do not have calculator with me here. I don't know who stole my calculator. I can't find it. So I had to actually perform a little bit of calculations to get that. Then we'll have -4 here. Then this one, to rewrite it in a square form, we'll have 1/2 square. And then this one, we can also write it in a square form immediately in this step. So it's going to be 1/√2, so that when we square that square root, it goes back to 2. Then from here, we can actually go and put it back. So what we need to notice, actually, this problem, let's do it with a square root. The original problem where I extracted it from, it had a square root. So let's do it with a square root. So from here, we will have integral of dx over the square root of, now, -4 square bracket, then x plus 1/2 square minus 1/2 square. Then we close the square bracket. Then from there, we can see that it is not allowed to actually take the square root outside of, to take the negative outside of the square root, because it will give us a math error. And then, or it can take us to complex functions, and we are not dealing with complex numbers right now. So we can actually, when we get to that part, this is still equal to that. So we can actually take out square root of 4 and then leave out negative there. Then we will have x plus 1 square, then 1/√2 all square dx. I've already written it. So we can see that square root of 4 is 2. So this can work out to the integral. We know that we are allowed to take out constant. So it's 1/√4. It's 2. Then dx. And then here, we must remember that we had a square bracket. That negative affects the whole situation there. So this side will have positive 1/√2 squared, then minus, we still have a square root here. We are working with a lot of square roots, so it's pretty easy to forget the square roots when you are writing them. So we have 1 plus square. So now I've reversed it by multiplying back the negative. Then from here, what I need to do is to go and check which formula corresponds this. So as I'm working here, I have my formula sheet with me here. So I'm looking for the one that has a square and minus f of x square, and it has a square root. So I found it to be this one, integral f of x square root a square minus f of x square dx equals arcsine f of x over a plus c. So that is the one that I found to use here. And then what can I do from here? I need to relate this formula to what I'm having there. So I can see that a in this case is actually 1 over square root 2. Then f of x, it's actually going to be x plus 1 over 2. Then f prime, when you differentiate there, it's actually 1. So it fits. So we can see that there on the dx, we only have 1. It's just dx. It's the same as 1 dx. So it's fine. But however, this one here, it can, since we have fractions, to avoid fractions, we can rewrite it in this way. So we'll have 2x plus 1 over 2. It's after we cross multiply. Then we will get that. So we will see how is this useful when we are going to plug back. So continuing now to plug back, I will simply say that I can take it as my original integral from the start, which was 1 minus 4x minus 4x squared. It's actually equal to, then I have that 1 over 2 there, 1 over 2. Then I will have arcsine, my f of x, I said is 2x plus 1 divided by 2 over a. My a, it's divided by 1 over square root 2. So this is why I chose to write it in this form, so that when I get to this part, it's easier to simplify when it's written in that way. So in most of the cases where we are having this type, we can rearrange them in that way. Then we will have 1 over 2 arcsine 2x plus 1 over 2. Then we can flip here by changing the division sign to multiplication sign. So actually here, it's divided by 2. Then when we change, we have square root 2 there. Then simplifying, we get that it's equals to 1 over 2 arcsine. So if we bring down the square root, it's actually going to be 2 minus half. Then we will have 2x plus 1 over, it's actually going here, we have 1, 2 to the power 1. 1 minus half is half. So we'll still have square root 2 here, plus c. Then let's look at another one. Perhaps we can look at maybe a simple one that is not very complicated. I wanted us to look at 5 integrals actually, to have a little bit of a picture and different formats of these integrals. So let's see, which one can we look at now? Let's look at something which is different from all that we've been doing here. Let me check from my notes. Okay, let's look at this type now. We are still completing the square. Let's see. No, this is not completing the square. Let's look for another completing the square. So we will have 4x plus 1. Now the dynamics will change. It takes a little bit of solving to do this type now, because at the top, all of the rest that we've been doing, we did not have a variable at the top. We're only having dx. Even here we only had 3, and 3 is a constant. Then even this one was a different format, but it did not have anything outside the square root. So here we had 3, here dx. So now we'll say this is number 4. So now at the top, we are having 4x plus 1. Then here we are having x squared plus 4x minus 12. And it's inside the square root. So we want to integrate this. So the best thing that we can do here is to initially split it into 2. So we can say that this equals 2. If we split it, we'll take the denominator there and divide 4x. So it's going to be x squared plus 4x minus 12. Then plus on the other side is 1. So it's going to be 1 over, then we have dx here, square root of x plus 4, x squared plus 4x minus 12. Then dx there. Then from here, we can see that all the time when we were completing the square, here we did not have x variable. So that x variable, it's going to give us a problem. But actually, let's go ahead and complete the square now. If we complete the square, we will have x squared. And remember, let's do it outside of the square root. For now, we'll take back everything after we are done completing the square. We will have x squared plus 4x minus 12. Then when we complete the square, how do we do it? We say we have x squared plus 4x plus the coefficient of the middle term, it's 4. 4 divided by 2, it's 2. So it's 4 divided by 2. Let's do it step by step. Minus 12 minus 4 over 2 all squared. Then from here, what are we having? What are we having? We'll have x squared plus 4x. 4 divided by 2 is 2. 2 squared is 4. Then this side will have minus 12 minus 4 again, like we did all the time. We can rewrite this in a square format. It's going to be x plus 2 all squared. Minus 12 minus 4 is minus 16. And then again also we can rewrite this like this, but it's fine. It's actually 4 square, or we can leave it as 16. It's not a big deal for now. Let's change our marker to black because we've been working with red. So this one now here, we can go and, since we splitted it already, we said it's 4x, then over. Now we put back the completed the square form. Let's just write 16 actually, because at the moment we won't be needing it. They still need a lot of simplification and some sort of substitution to solve this problem. Then plus square root of 1 over x plus 2 square minus 16 dx. So what do we notice? We can see that this term here now, this one, it's actually doable by the formula. And it simplifies to actually looking at this, it's going to be, it's an Akkosh. So for this one here, maybe you can put 4 square. Then a is actually 4. Then f of x, it's actually x plus 2. Then you go and read, there's a formula for that, which is Akkosh. But for now, let's see another method that we can use. So the reason why is because we cannot integrate one side alone. We have to integrate both of them to have a full marks. If you integrate that one only, you will not get all the marks in there when you are writing your assessment. So we can actually use a method called U-Substitution. This method changes everything now. In what was x now will be in terms of u. So we can say that there under the square root, we can take that x plus 2 and make it u. So u is actually x plus 2. And again, solving x here, it gives x equal to u minus 2. Then I will come, because the main problem, it's actually that 4x. Let's replace that x with u minus 2. So now here it was dx. So let's work with du now. And then according to this substitution, then we will let our dx to be du. Then we will come here. So in the place of x plus 2, we put u squared minus 16, then plus, let's change this one, although this we can integrate, but let's continue with substitution so that we do not have, I realized that on the previous problem I did, I was using U-Substitution, where on the other term I was having x variables, because this one I just integrated by Akkosh, while this other one I was working with U-Substitution. Then from here, this is going to be u squared minus 16 as well. Then here we can distribute that 4 there. It becomes 4u minus 8. So du is still there over the square root of u square minus 16 plus integral of 1 du square root of u square minus 16. So it seems a little bit long, but if you carefully look at it, you will see that it's just not that very difficult. So now we can split this term into two parts. We can divide 4u and minus 8 there so that we can see what happens after we do that. Then when we do that, we end up having integral of 4u over the square root of u square minus 16, then minus 8 integral du here also u square minus 16. Then on the other side we had plus integral of du over u square minus 16. So we have just splitted the left side by dividing both sides by the denominator. Then what we notice is that now these two, they are the same. So it's like negative 8 plus 1. It's going to give us negative 7. So this side will have 4u du over square root of u square minus 16. Negative 8 plus 1 is negative 7 du over u square minus 16. Then again also this 4, I can write it outside the integral because it's a constant. Or we can leave it there actually. Let's just leave it there for now. It does not help us to take it out. So we can see that this now is an integration that we are familiar with, and we can see that by, instead of taking out 4, we can take out 2, then so that we are left with 2u. Then that square root on the denominator, we can take it up and rewrite it in this form, so that now it's to the power negative half. If we take it up, the square root, because we know that square root is actually 1 over 2, then if we take it up, it becomes negative 1 over 2. So 4, I've written it in terms of 2 times 2, which is still the same thing. So I can see that now here, there is a formula that we can use here, which says integral of f prime f of x prime, then f of x to the power n, and then provided that n should not be negative 1, and we can see that now our exponent there is not negative 1, it's negative half. So this formula can work. So here, this formula has dx. It says that if you're having an integral that looks exactly like that, what we need to do is to say f of x to the power n plus 1 over n plus 1 plus c. Then this side will just have a cosh u over A plus C. So because now U is our f of x, it's the same as f of x over A. So what we can say is that in this case here, on the first term, if we say that our f of x is u squared minus 6, then f prime corresponds to, when we differentiate that, we get 2u. So the formula can work out perfectly. So what we need to do from now, let's erase this. We are having negative 7 du over square root u squared minus 16. So this whole thing, when we integrate the first part, we will use the formula there. So 2 is outside the integral. Then we will have minus 16, negative half, because our n is negative half. So negative half plus 1 is just going to be half. Then we divide by negative half plus 1, which gives half again. Then minus 7. This we said that is going to be arc cosh u over A plus C. Then 2 divided by half. It's the same as actually saying 2 multiplied by 2, because you will take the 2 up. So it will make this to be actually 4. And then this can be written as, because it's a square root, it can be written like that. Then we have arc cosh u over A plus C. Then we can see that this one here, we have replaced it, and it was actually what we had from the beginning. It was actually this. So we can actually just say this is the same. It was actually what, x squared plus 4x minus 12. So it was x squared plus 4x minus 12. And when we remember, we said that our u was x plus 12. So we don't need to try and put x plus 2 in the place of u to try and take it back there. We can just know that we actually completed the square here. So this is the same as x squared plus 4x minus 12. This is a cosh. Then we have x plus 2 in the place of u. And then our A, it's actually going to be 4, because 4 squared is 16. So actually here I was supposed to have u over 4 plus C. So that's it. We have, it's a long problem. It requires a little bit of thinking. So that's how we use U-substitution. The moment we have a variable at the top, it may need some sort of manipulation. But it's not all the time that when we have a variable at the top, we will need to manipulate. So let's look at the last problem, and then I believe this will be problem number 5, and it's actually the last one. So how about if we are having x plus 3? And if you are tired, you can pause the video and take a break and try to digest what you've been learning, and then you will continue after. So when we're having this, the moment you deal with these integrals, you will be able to actually know what to do the moment you look at the integral. Just do different kinds of integrals, then you'll be able to know exactly what to do. So this one now, we can split it into two again, like we did in the previous one. The only difference is that now we don't need to complete the square. The denominator does not need completion of the square. So we'll have x over square root 1 minus x squared dx plus 3, and 3 we can take it outside the integral, over 1 minus x squared. So that's how we can split that into two. Then when we go and check, is that now this one now can be written as x into 1 x squared dx plus 3 integral. Then I will explain the reason why I wrote it like this. This takes exactly the previous formula that we used, the one that looks like this. It's actually the first formula of integration. It's the most basic formula of integration. It's like that. Then we said that it gives f of x n plus 1 over n plus 1 plus c. Then this side, what are we having this side? This looks like f prime a square minus f of x all square. Then on that case, I can see that my f of x, it's 1 minus x square. Then f prime x, it's actually 2x. But there, I only have x. So I can actually put the 2 here. Then I know that putting the 2, I have to divide by 2. Then let's look at the other one. Here we can see that our a is actually 1. Then our f of x, it's just x. Then the answer to this now becomes, we'll apply this formula to integrate this, and then this formula to integrate that. So that 1 over 2, it's still there, which is the constant. So now we can see that our formula matches exactly the problem there. What we need to do is to write our f of x, which is actually 1 minus x squared, then to the power negative half plus 1 divided by negative half plus 1 plus this one goes to what? This is an arc sign. I didn't write this for this, but I think we worked with it on the previous example. So we have arc sign. Our f of x is actually x. Then our a is 1. Then plus c. So we can see that this works to 1 over 2, 1 divided by, to the power half. Negative half plus 1, it's a half. Negative half plus 1 is still half on the denominator, plus arcsine x plus c. So a half divided by half, we can see that it's actually 1. It's the same as if we take the 2 up, it will divide with the 2. So this side here we will be left with square root of x squared, then plus arcsine x plus c. So that's it for today with these integrals. We had looked at a couple of integrals that were different, but the first 4, they required us to apply a completion of square, and then the 4th integral that we looked at, it required us to do completion of square, but we also had to use a U-substitution. So please stay tuned on the channel. Please subscribe and like these videos so that when I upload another videos you can be notified. Thank you.